Hello and welcome to my literature review of X-ray diffraction and carbon nanotubes. What are carbon nanotubes? Carbon nanotubes are a form of ordered carbon, which is equivalent to a single layer of graphene that has been rolled into a cylinder, which can range in diameter from 5 nanometers to 100 nanometers, and length typically in the order of a few hundred nanometers, but have been grown up to 50 centimeters in length. They were first discovered in 1952, and in the last 2 decades have seen an explosion in applications and synthesis. High-quality carbon nanotubes are often produced by chemical vapor deposition under full or partial vacuum. Pyrolysis of various hydrocarbons have also been shown to produce large quantities of carbon nanotubes, although often in a wide range of quality. Their applications range from structural, such as composite materials, energy applications, such as battery cathodes or hydrogen storage, medical applications such as drug delivery systems, and electronic applications such as sensors and capacitors. This unique nanomaterial is most often noted for its incredibly high strength-to-weight ratio, about 100 times that of steel. It also exhibits very high stiffness at 1.2 terapascals and great fatigue strength, which is with high tolerance to large strains. They can survive temperatures up to 3,000 degrees Celsius and can transport a great deal of heat and electric current. Their electrical properties can vary from highly conductive, even superconductive, to semiconductive. The range of properties for carbon nanotubes are all highly dependent on their structure, and geometry of carbon nanotubes do not have a single structural format. There are several key geometric considerations for nanotubes. The most obvious are diameter and length, which will have considerable effect on the strength and flexibility of the nanotubes. The second most important is what is called chirality of the nanotubes. This is the orientation of the carbon lattice in relation to the axis of the carbon nanotube, and it is represented by the integers n and m, and can be used with the unit cell vectors a1 and a2 to determine the chiral vector, designated as CH. A carbon nanotube with a chirality of n and 0 is so-called a zigzag nanotube, and one with a chirality of n equal to m is so-called an armchair nanotube. The angle between the chiral vector and the axis of the nanotube is called the chiral angle, theta. Carbon nanotubes can also be single-walled or multi-walled. The multi-walled carbon nanotubes are considered to be either concentric tubes, which is referred to as the Russian doll configuration, or spiral, which is sometimes referred to as scroll or jelly roll. The geometry of the nanotubes, which is repeating hexagonal lattice, make layer spacing in Russian doll configurations tightly controlled by the chirality. The spacing between multi-walled carbon nanotubes therefore has a theoretical limit and can greatly affect the strain tolerance of the nanotube. For all these reasons, understanding the geometric characteristics of your nanotubes that you wish to work with is critical for predicting your properties. Classifying carbon nanotubes has been done by scanning electron microscope, Raman spectroscopy, thermogravimetric analysis, and X-ray diffraction, with each technique offering unique perspectives on the nanotubes. X-ray diffraction has been shown to be an effective measurement tool for the chirality of nanotubes, the interlayer spacing, and the structural strain, as well as the thermal expansion of the nanotube lattice. Indirectly, the diameter of the nanotubes can be calculated as it is strongly correlated with the number of layers and interlayer spacing of your nanotubes. Although carbon nanotubes are often referred to as non-crystalline materials, they are far from amorphous. The repeating hexagonal carbon pattern means that the diffracted peaks from the carbon atoms can be used to determine specific details of the nanotube, if the results are considered as aligned graphene sheets. X-ray diffraction results can be predicted by considering the scattering of multiple carbon atoms, which has been well studied, and applying it to a helical structure, using the equation form shown here. Since the carbon nanotubes are highly directional, the orientation and morphology is critical to the results of the diffracted peaks. The primary peak seen with carbon nanotube diffraction is the 002 peak. This is a high incident angle reflection and can be correlated to the interlayer spacing of the carbon nanotubes. This shows up in multi-wall carbon nanotubes as well as single-wall carbon nanotubes, though in the single-walled case, it is generally caused by diffraction from the near and far side of the cylinder. The 002 peak can be used to determine the interlayer spacing by simple application of Bragg's law. If the carbon nanotubes are aligned in such a way that the X-ray is parallel with the axis of the tubes, then additional HK0 peaks will be present in the diffraction data. The scattered HK0 peaks present at higher degrees of incidence are a result of the hexagonal lattice of the carbon atoms, which make up the walls of the carbon nanotubes. Single-walled carbon nanotubes are the stronger variant of nanotubes and are also generally harder to produce. Their structure does not have many complications besides the standard diffraction results, but identifying single-walled carbon nanotubes versus multi-walled carbon nanotubes can be performed using X-ray diffraction. The position of the 01 peak in the translated diffraction data has been shown to be useful in determining the type of carbon present. Since the interlayer spacing is abnormally high for a single-walled carbon nanotube, the peak position is shifted to a lower Bragg angle of 26 degrees instead of 26.5 degrees as seen with disordered graphite. Consequently, a resulting Q value for single-walled carbon nanotubes of approximately 0.43 is a strong indicator of this form of carbon. In the diffraction data, the secondary peaks after the 002 are what define the multi-wall carbon nanotubes. These secondary peaks differ from graphite in that the peaks are broadened and smeared compared to the sharper peaks produced in graphite. In multi-walled carbon nanotubes, there are only certain chiralities which can exist to maintain intershell distances within the theoretical limits of 0.344 and 0.36 nanometers. Thus, there is a relation between layer spacing and diameter. Qiang et al. Determined this empirical relation shown here for that spacing. This is derived from the Russian doll style of concentric multi-walled carbon nanotubes. If a scroll-type multi-wall carbon nanotube is present, then the interlayer spacing will violate this rule. Also, due to the free ends of the scroll nanostructure, the interlayer spacing can change anisotropically over temperature, therefore taking multiple diffraction measurements at different temperatures, and comparing the interlayer spacing can be an effective way to determine the multi-wall carbon nanotube is scroll or Russian doll. As can be seen here, the 002 peak shifts as you increase in temperature. As mentioned before, one of the basic parameters of carbon nanotubes is its diameter. The 002 peak can be used to determine this using the Debye-Xray method shown here. This is of course an average of the particles present and is also dependent on which carbon nanotubes are oriented properly for this diffraction. It has been shown experimentally that the d-spacing gets smaller as the diameter increases. This is due to the lower lattice strain in the carbon nanotubes, which have a greater curvature. An empirical relation has been derived for this shift in d-spacing based on diameter of single-wall multi-nanotubes. In terms of multi-walled carbon nanotubes, with more layers causing more scattering of the 002 peak, it tends to be broader than single-walled carbon nanotubes, making diameter calculations less accurate. But it was found that the Bragg angle increases and the full width half max decreases for the 002 peak as the diameter gets larger. This is also a strain factor which plays into the diffraction, but could potentially be lattice alignment being more ordered for larger multi-wall carbon nanotubes, thus reducing scattering. Highly aligned carbon nanotubes are important for certain sensors and energy applications. X-ray diffraction is able to detect alignment of nanotubes due to the highly directional nature of their diffraction. For example, as the sample rotates, the incident beam will scatter downwards when it hits vertically aligned carbon nanotubes. However, when it hits horizontally aligned carbon nanotubes, the beam will scatter upwards. Note that only upward scattered diffraction can be measured by the sensor. Thus, the 002 peak will decrease significantly as the nanotubes are better aligned. This is seen here, where the aligned specimen has a much more diffuse peak than the randomly aligned specimen, which has a much sharper peak. Chirality is important because it can have a large effect on the properties of the nanotube. For example, the transition from conductive to semiconductive is based on chirality. Nanotubes with an n minus m equal to 3q, where q is an integer, are metallic, whereas those with n minus m equal to 3q plus 1 are semiconducting. Theoretical calculations for the diffraction of carbon nanotubes with different chiralities were determined, and it was found that there should be present certain peaks specific to some chiralities. For example, for armchair chiralities, there would expect to be sharp peaks between a Q value of 5 and 6, whereas for zigzag chiralities, we would expect distinct peaks between 3 and 4. Experimental values were able to include some degree of chirality identification once a background signal of pure graphite was subtracted from the measured results. The sharpened peak correlating to the specific armchair chirality was determined for the metal-enriched carbon nanotubes, which were predicted to have a higher degree of armchair chiralities. Strain broadening can complicate the calculation of nanotube diameter as well. The smaller the diameter, the higher the curvature of the nanotubes, and the higher the strain on the carbon lattice. This will result in peak shifting and broadening. It was predicted that the broadening of the 002 peak would be lower for larger diameter nanotubes, and it was found that a decrease in full width half max, aka the breadth of the XRD profile, with increasing diameter was consistent with lower strain and curvature of the larger diameter nanotubes. Here you can see from the two charts that as the diameter increases, the peak profile becomes sharper and less diffuse. Here is the strain broadening correlation. While X-ray diffraction has shown to be an effective method for some characterizations of carbon nanotubes, there are still challenges to overcome. For example, X-ray diffraction is a bulk analysis and over an average of a large number of nanotubes. Thus, characterization of specific nanotubes is difficult to do. Orientation can also greatly affect the diffraction, and this is an issue because most carbon nanotube synthesis processes result in a high degree of orientation, especially with single-walled carbon nanotubes. Noise from amorphous carbon and graphite particles can greatly reduce the intensity of the peaks. This can be seen here in some of the peaks for the calculated versus the experimental. Strain differences between carbon nanotubes of different diameter will also shift and broaden peaks, making characterization of nanotubes with a broad diameter distribution difficult. Thank you for joining me for my partial review of carbon nanotubes and X-ray diffraction.